Hi, welcome to Operon Regulation, a visual guide with your narrator, Joe Pham. So essentially, Operon regulation is performed by DNA binding protein. There's two types of control, negative and positive. So first, let's talk about negative regulation. Negative regulation generally involves a protein called a repressor. This protein binds to DNA at the operator site and makes it hard for transcription to occur. Let's introduce the main player in gene transcription, RNA polymerase, otherwise known as RNAP. So, think about this guy. Without any regulation, RNAP will do its job, moving along the DNA to transcribe mRNA, leading to a product. So what happens during negative control type 1? There's a repressor in the way, and RNAP can't get through. However, a co-inducer, the C stands for co-inducer, can interact with the repressor, removing it from the mRNA, allowing RNAP to bind and do its job. A more complex example of this control is the lac operon. The lac-I repressor is a tetramer protein that's bound at 3 operator sites upstream of the operon, O1, O2, and O3. The lac operon is always expressed at basal amounts. This means that even with the repressor present, the product can be made. The product in this case is beta-galactosidase, an enzyme that can cleave lactose, in this case an apple. Beta-galactosidase cleaves lactose into glucose and galactose. Galactose is in equilibrium with allolactose, which is a co-inducer for this operon. An allolactose interacts with each of the 4 subunits to remove the repressor from the operon. Without the repressor in place, more and more beta-galactosidase can be produced to cleave lactose. What happens in type 2 negative regulation? The repressor in this case is inactive, that is, until the product builds up. With an excess, the product will act as a co-repressor, moving the repressor into place and blocking RNAP. So now we can move on to positive control. Positive control involves an activator. So let's start with type 1. Imagine that RNAP is a lazy worker, and the activator is a lazy manager. The activator is normally not active, but with the help of a co-inducer, the C stands for co-inducer, the manager or activator will be activated, inducing the lazy worker to do work. In type 2, let's imagine that the RNAP is someone that always has positive support with them. This is the activator. If there's a co-repressor present, however, the activator will be inactivated, and the RNAP, with no more motivation, will cease to do its job. Now let's move on to a different mechanism of operon regulation, catabolite repression. Catabolite repression essentially means that glucose will always be used as a primary energy source. This means that while glucose is around, catabolite-sensitive operons will not be transcribed, such as the aforementioned lac operon. Once glucose runs out, there's a higher concentration of the phosphorylated version of the protein, 2A superscript gluc, which in turn activates adenylate cyclase, the enzyme that produces cyclic AMP, otherwise known as CAMP. The activation of adenylate cyclase causes the concentration of CAMP to increase. This is where another protein comes into play, the catabolite gene activator protein, otherwise known as CAP. CAP will interact with two CAMP molecules to form a CAP-CAMP2 complex. When there's a lower concentration of CAMP, the RNAP doesn't bind as efficiently. This leads to sluggish transcription even if the repressor is absent. But when there's a high concentration of CAMP, the CAP-CAMP2 complex will form and bind to the -55 to -70 region upstream of the operon and change the shape of the DNA to favor closed promoter complex formation. This allows RNAP to finally transcribe the gene at maximum efficiency. So going back to the lac operon example, this would mean more beta-galactosidase produced, meaning more lactose cleaved, more allolactose co-inducer made, leading to even more transcription of the operon. And essentially, this concludes what we have to say about operon regulation. This has been Operon Regulation, a visual guide, narrated by yours truly, Joseph Pham.